The last lecture of this morning's session is by Eran Maniv from the School of Physics, and he's a student of Yoram Dagan, and that's a student talk, of course. And it's about tunneling into quantum confinement, creating by single-step nanolithography of conducting oxide interfaces. Eran, please. Thank you.
Okay, thank you very much. First of all, I want to thank the organizers for inviting me, and I'm very excited to be here. As you said, I'm Eran. I'm a student of Yoram physics, different from what we heard till now, I think. Let's start. The talk I'm going to give now is about a quantum dot we created and a new nanolithography technique that we actually developed in the Nano Center. And this is the people who were collaborating. It was published 1 year ago in PRB. Okay. So my outline of the talk will be introduction. I'm going to introduce conductivity in 0 dimensions. After this, I'm going to give a motivation for the experiment. A little background about the material we grow in our lab, STOLAO. The challenges of the fabrication and the methods we developed. A bit of results and summary. So, when we talk about conductivity in 0 dimension, what do we mean? Eran Sela talked a bit about it yesterday. I'll elaborate about it. If we want conductivity in 0 dimensions, we need to actually confine electrons in all 3 dimensions, but this has to be with respect to the relevant length scale. And the length scale itself is actually the wavelength. As you know, particles have wavelengths, and it's related to the de Broglie equation. And as you can see here illustrated, if you do that, an island is created in all 3 dimensions, and it is connected to contacts with weak links, and electrons can only tunnel into it from the contacts. On the left here is a fabricated device from semiconductors, which illustrate 2 quantum dots. What happens after we confine the electrons in all 3 dimensions? A potential well is created, and in this potential well, only discrete energy levels are available to populate this isolated island. Why is that important, actually? Because if we want now to populate this dot, we need to actually equivalate the energy of the contacts with the energy levels of this dot, of this island. And whenever we'll do that, a resonance will appear, as you can see here in this nice measurement a long time ago, in the conductivity. And you can do that with 2 different ways. You can do that by changing the energy of this quantum dot, let's say the energy with the gating from backgate or from top gating. Or also you can just change the bias on the drain source of your contacts from left to right. And by that also equivalating the energies of those contacts with the energy of the quantum dot. Additionally, not only those energy levels are important, but also something that's called Coulomb repulsion is important. This is the charge in energy that's related to the capacitance of the system. And because of repulsion between electrons in the dot and outside of the dot, it means that dependence on the capacitance of the system, it will need maybe more energy to populate electrons in this dot. So this is a bit about quantum dots. The motivation of our experiments is semiconductors, which probably you know well. High quality materials, silicon, gallium arsenide, and they actually show various studies of mesoscopic phenomena, such as what Eran showed you yesterday, quantum wire with conductant steps, or quantum dots, I'm going to show you today, here fabricated on gallium arsenide, with the nanolithography techniques and electrostatic gating, giving you this Coulomb peaks, or resonance peaks. But on the other hand, this is a very simple model, okay? And no interactions are introduced here between electrons. What we want to investigate or study is to combine these devices with a strongly correlated electron system And we think this is the next step towards study of new physics. What we suggest is something that we have in the lab, and we think is very interesting, is perovskite oxide interfaces. Actually, these are all kinds of oxide interfaces with this structure that have a lot of various phenomena, such as ferroelectricity, ferromagnetism, superconductivity, and many more. Not only they possess all those interesting phenomena, also when you combine them and you grow them one on top of each other, you can get a new interface with new phases. And on one of them I want to elaborate. This is the STO-LAO. This is a material we grow in our lab in pulsed laser deposition. First found by Tomo and Wan in 2004. What is that? It's two band insulators, so it's two insulators, lanthanum aluminum oxide and strontium titanium oxide. But when you grow the lanthanum aluminum oxide on top of a TiO2 terminated STO, you get a conducting interface, which is actually two-dimensional, okay? I want to stress that if you don't grow it epitaxially, it means that the lanthanum aluminum oxide is not a single crystal now. You get an insulating interface, and this can help us actually in our fabrication. Why is this material interesting besides that it's two dimensions, conductivity? It is highly correlated. What does it mean that it's highly correlated? It means that the electrons have interaction between themselves. How can see it in experiments? So first of all, this material is superconducting under 350 millikelvin. This is the first measurement that showed that. Second of all, it's ferromagnetic. This is Scanius grid from Bina Kalaski a while ago. Moreover, it has spin-orbit interaction. It means that the orbital momentum of the spin has interaction with the orbital momentum of the electron has interaction with its spin. This is measurement from our lab, Moshe Ben Shalom. And also it has interactions, Coulomb repulsion interaction between different bands that actually change the band structure itself. So it's really interesting, and it has a variety of phenomena that show it's highly correlated. So we have the material, and now we just need to go from 3 dimensions to 0 dimensions. And as I said before, the relevant length scale is the Fermi wavelength, which actually depends on the energy of the Fermi energy of this material. And it's in our material, it's 10 nanometers, really small. So from 3 dimensions to 2 dimensions, it's really simple because this material is already 2 dimensions. A lot of studies show already that the conductivity is under 10 nanometers. If you want to go to 1 dimension, you just really easy. It's not really easy at all. Create a 10 nanometer trench. And even going beyond 1D is possible, and I'll show you this in a minute. The challenges, on the other hand, are really big. First of all, STO itself is insulating, so it's really hard to write on it in the E-beam. And second of all, it's dry etch sensitive, so if you ion mill it, it will become conducting. Second of all, if you talk about LAO, it doesn't wet etch, nothing. So it's really hard to work with it. And the position, we deposit the LAO in 800 degrees, is destructive for most resists. So it's really hard to work with these materials. What has been done till now? So it's something that's called amorphous mask process. The main idea of this process is that you do your lithography, but you deposit an amorphous LAO in room temperature, and this mask will be your negative mask. And after this is like the gray part here, you lift off, and after this you can just deposit your crystalline LAO, and it will be conducting only the green part here and not on the red part here. So this has been done for a few years already, but it has a lot of disadvantages. It requires several steps, it's low yield, and it has finally a limited resolution because of all these different steps. So a need for a better process for oxide is required, and this is what we proposed, a new method combined with hydrogen silicon, which is actually something that's called HSQ. It's something that we found when we talked to Ron Koskov from the Nano Center, and actually this resist is the resist they use to demonstrate E-beam capabilities, but they don't have a lot to do with it except for all those demonstrations. But for us, it's actually perfect. it results in a hard and insulating mask of amorphous silicon dioxide. And what we do is this HSQ process. We take the substrate, we pattern the HSQ, develop it, and immediately can deposit the crystalline LAO, and it will be only conducting on the part where there's no HSQ. So this method actually requires only a single step of lithography and deposition. It minimizes the contamination effects, and it can reach, if you have the right E-beam, resolution up to 7 nanometers, which is really good. So after we thought of this, we just went to the E-beam in the Nano Center and wrote a device. This is the first device we wrote. It's a hole bar. The dark parts here are just the HSQ, and the lighter parts are the lanthanum aluminum oxide deposited on the STO, and it is the conducting part. You can see the contact configuration. If we zoom in, we can see the constriction inside this hole bar, which was motivated from semiconductors, as I told you before. And even if we go zooming in, we can see the order of magnitude, which is 100 nanometers. Not only that, we want to see that this interface is clean, or the surface is clean after all this new method. So we did a AFM scan before deposition and after development of this HSQ. And after deposition of LAO, and we saw our atomically smooth STO or LAO, which showed that no contamination has occurred on our material. So we got the device, and what we'll have to do is take the device and cool it down in liquid helium, and this is what we've done. We had 3 different devices, 3 different sizes, 100 to 200 nanometers, and we cooled them down in pumped liquid helium to 1.5 Kelvin. What you can see here is the resistance in mega ohms versus gate voltage. As I said before, you can change the backgate of the STO, and by that changing the energy of, let's say, the electrons or the carrier density of electrons. And the normal plot will just go monotonically up by depleting electron. But this is just something different. Here we see on a certain onset that actually corresponds to the size of this constriction, a pattern of dips and peaks, which actually resembles some kind of tunneling effect. And when we got this, we thought we were having something really interesting. So we went and want to do the main measurement you do when we think you have something like a quantum dot. You measure the IDV measurement and try to see a diamond plot. And this is what we did. This is a measurement in 160 millikelvin in the dilution refrigerator. And the color code here is the IDVs, the conductance. And y and y-axis and x-axis is just the biases. It means on the y-axis we put the bias on the drain source, and on the x-axis it's the previous one. We just put voltage on the back gate. And what we see the same phenomena on the x-axis and the y-axis, which means we have tunneling in both directions. And we can see this resembling diamond plot, which is a main characteristic of a quantum dot. So we got the main result. Other issues I want to discuss is if you remember the Coulomb interaction and charge energy, in our system, the charge energy is negligible, and it is because the dielectric constant is huge in STO, and because of this, we don't have to rely on it at all. And what actually it means that we have a direct spectroscopy of the energy level, because we don't have to take into account this charge in energy. And by that, we can just count the spacing between those Coulomb peaks and calculate, as you can see here, the energy spectrum. And from that energy spectrum, we can actually estimate the size of this dot, which is actually 5 to 10 nanometers, and it's self-consistent with the Fermi wavelength under 10 nanometers. So I just want to summarize. We developed a new and simple lithography method for oxide interfaces. It enabled us to create and characterize a quantum dot. And new and exciting mesoscopic experiments can be studied in the future. I'll leave you with that. Thank you.
Thank you, Eran. The paper is open for discussion. Amit.
What is the nature of the quantum dot? To make it compared to more common semiconductors, such as cadmium sulfide and stuff like this? So are there levels or?
You mean what's the properties of the quantum dot? So this is just an initial measurement, and actually the system is much more complex than what I showed here. We have a lot of other effects on it, so it was really hard to characterize, like, let's say, much more advanced phenomena in this quantum dot. And this is a study in progress. The main point I wanted to introduce here, that we can actually use this new technique and get much smaller effects on our large-scale STO-LAO interface.
I have a question. How do you translate the bias voltage to the real
To the
change
energy.
in the
Okay,
biasing
so
of?
there's a conversion factor you have to calculate, and you can do it with temperature dependence, and we did it. I didn't show it here. And you can do it also with the slope. With those diamond plots, you saw that there's a slope between the drain source voltage to the gate voltage.
Right.
So there's all kinds of systematic ways to do that. And it's not, as you say, it's not the gate voltage itself.
Okay,
the
it's
measure.
not a free parameter. You have that in mind.
Yeah.
The conversion. Okay.
Yeah.
Thank you. Any other question? Okay, so it's very rewarding to be a student at Tel Aviv University. And again, a present to you. And let's thank all the speakers of this morning's session again, and coffee break.